Good evening. I'm Ted Maxwell. I'm senior scientist here at the National Air and Space Museum, and I'd like to welcome you to the first of the 2011 Exploring Space Lecture Series. It promises to be a great series. We're just absolutely thrilled to be able to bring it to you live. We have some fabulous lecturers this year, and as you've heard a little while ago, we're going to start off at the center of the solar system and look at some observations there. Now, being a federal institution, and you all know about the federal budget, you know that we could not possibly do this ourselves. And therefore, we have some really well-meaning sponsors that we've had, some of which have been around for several years. And I'd like to acknowledge Mike O'Hara. Mike, I thought I saw you over there. He's with Aerojet Corporation, and Aerojet is the principal sponsor for this year's Exploring Space Series. And in addition, of course, you know, none of this would be possible without NASA. And I think Lika and Hashima, did I see you somewhere over here? We also appreciate the long-term support of NASA for the series. So it's really, and you know, being inside the museum. Two other people you really ought to know about. One is Priscilla Strain, who organized this year's series, and Priscilla is right down here. And the other, who has managed to disappear, I believe, is Jean DeStefano. And she is the one, when you have problems with tickets or want to get in instead of being an overflow, and you want to complain to somebody, she's the one that handles all those things. So we really appreciate Jean and her help. So those are the folks inside that make it happen. Tonight, Dean Pesnell is really, as our first speaker, he received his PhD in physics from the University of Florida. And since 2005, he's been an astrophysicist and Solar Dynamics Observatory project scientist at NASA Goddard Space Flight Center. And tonight's lecture, the Solar Dynamics Observatory, the Sun Close-Up and Personal, is, as I said, a start to this year's series. The SDO is the first mission to be launched for NASA's Living with a Star program. And it's a program designed to understand the causes of solar variability on various timescales. So we're going to be looking at it from minutes to years to decades, for many years to come. And hopefully it'll eventually key in on that billion years. Maybe it's really only 995 million we have to worry about, but we'll find out about that. So Dean, it's great to have you, and we appreciate your being lead-off speaker in the series.
Oh, it does work. Okay. Thanks for inviting me here. I've been to the Smithsonian a couple of times. I always wondered what it would be like to stand down here, and now I know. When I stand here and talk about the Solar Dynamics Observatory, I represent a large group of people. I represent the hundreds of engineers that built it, and the 100 or 200 or so scientists that are looking at the data on a daily basis. And there's also the program that built it, the Living with a Star program, and then there's going to be more missions within that program. I have the advantage, I only have to talk about one, this one, the prettiest satellite ever launched. I have a model of it down here that you can admire it in its duct tape-like beauty. Okay, so why study the sun? You all care. Okay, you use the sun on a daily basis. It gets you up in the morning. It puts you to bed at night, unless you're reversed. That's represented by that upper left. In the lower left, we have art. The sun has always inspired people to make drawings of it. This is one of my particular favorites. This is, it appears to be an eclipse. This is by an artist named Moreau. He never really explained what it was. It's on next to a page of French poetry that has nothing to do with it. So he evidently drew a lot of pictures of the sun, and somebody else drew a lot of or wrote a lot of poetry, and they put them together in a book, and they don't actually appear to mean anything. But it's fun. We have Barbara Thompson at Goddard collects these different kinds of things that show the sun in its various things, and one of those is the upper right. That's religion. Almost all civilizations have held the sun in some sort of position in their religion. And having been brought up Baptist, it's in the Baptist religion too, because the sun was as pure and on something light. It's been a while. But rather than that, I have an example. That's the Assyrian sun god Shamash in the upper right. And then in the lower right, something we're going to see later, so I thought I'd introduce it before the movie. We have what are called parhelia. And these are little bright spots that show up around the sun, especially during the cold weather and in the winter. And I see them when I live out near Annapolis, and when I'm driving the final road up to my house, I can often see what's called a sundog. And it's a little bright light off to the side of the sun. It happens to be these guys here, and there's another one over here. But this is a particularly good display. It has all kinds of other reflections from ice crystals in space. And they're called sundogs because they follow the sun, and that's what we call everything. But the cool thing about the sun is that at some point, somebody realized that every once in a while it disappears. And for no apparent reason. There's an eclipse. Now, if this is your religion, that the sun is very important to you, and all of a sudden it goes away, that's a problem. And in particular, the religious group that you're associating with would now like to know when the next one's going to be, so that they can go out and take care of it in their particular style. Now, this is the birth of astronomy, is the ability to predict eclipses. And when we look back in archaeoastronomy back in the 10,000 year range, we see people trying to build observatories that may or may not have been able to predict eclipses. We can run our fancy computers and figure out how to predict an eclipse with Stonehenge. It's not obvious that that's actually what they used it for, but there is some possibility that they built that thing so they could do eclipses. So, in the early 1600s, a guy named Galileo shows up. He's not the first guy to see these dark spots on the sun, but he's certainly one of the guys that makes it popular. Galileo is the guy. The thing in the middle is a picture of the sun from his notebooks, and I think these are from 1613 or something. Yeah, 1613. Look at that. The sun is not unblemished. And they spend quite a few years watching these things. And here's a summer of his observations. And this is a really great little archive over at Rice University. And they made the movie too. It was even easy that way. And you can see a couple of things right away you're going to have problems with if you think the sun is unblemished. Not only are those things there, they move and they change. These are sunspots. This is what we care about nowadays. We have now looked at the sun in many different ways. It's one of the first objects ever photographed. Why? Because it's bright. And if you have a really lousy camera and you want to take a picture of something, the sun was a great place to start. And so the first photograph is taken in 1843. 2 years later, we have a whole series of pictures taken of the sun. We continue looking at the sun in very many different ways because it is a good object to do those first things with. We built special telescopes starting in the early 1900s that allow us to look at the sun in very narrow bands of light, and these are where just a single element is contributing to the light. This was an element called hydrogen. It's the most common element in the sun. And you'll notice that we're starting to see some really cool stuff here. Not like just those sunspots. As a matter of fact, sunspots in H alpha look bright. And so we already have some problems here understanding what's going on. What do we look at the sun like now? This is our latest view of the sun. This is 7 months of solar observations from the AIA instrument on the Solar Dynamics Observatory. Now, there are few screens in the world big enough to really appreciate these images because we take them in a very nice high resolution mode and then we put them together, and this was done by Ralph Seguin out in Palo Alto, California. And it just basically shows us the sun from about May 1st through the beginning of November of last year. It's just a very nice summary movie. And you could sit, and believe me, you can sit and stare at this for quite some time. We don't have that option. I do have to get along, but we will see some more of these later. I just want you to see there's places where the sun is bright, there's places where the sun is dark, and none of this light is visible to your naked eye. This is all way out in the ultraviolet frequencies, ultraviolet wavelengths. You can't see them, but we can take pictures of them and then convert them into colors that you can see. Why do you care? Because every once in a while the sun burps, and here's one of them. There it goes. It throws off a big mass of stuff, and that mass of stuff comes over, and in this case, it interacts with the magnetic field of the Earth and causes pretty aurora. It's great. It's a nice picture. The universe is so happy. Of course, I wouldn't be here, and we wouldn't have spent money on a spacecraft if all it did was create aurora. Actually, the material that comes off the sun can be quite destructive, depending on when and where it gets to the Earth. So, why SDO? We've developed a science called space weather. We had a great example. I think I had the date wrong. It should be April 8th, 2010. Otherwise, I'm telling you it's going to fail in a month. Probably should have fixed that. About a year ago, a spacecraft just stopped. Now, anybody here ever see television? Okay. Anybody here ever use satellite TV? You know, you point your antenna at a spacecraft and you never have to move your antenna again. It's great. Okay, those are in a special orbit called geostationary. And you're able to point your antenna at that and never move it because the satellite appears to remain motionless, suspended and motionless above you. That's a precious piece of space real estate. There's only one narrow band around the Earth where that's true, and this spacecraft is in the middle of it, and it decides to go for a trip. And it just starts wandering through that belt, and it has all these other satellites up there that people are using their TV with, and they have to keep moving those satellites around in a little dance so that they don't get whacked by this Galaxy 15. Now, Galaxy is really good because they had another one failed about 10 years ago that took out pager service across North America. Once again, it was a problem caused by something related to space weather. We never really do find out what actually happened. But we do know that we've had at least 4 where they've either lost a spacecraft or lost considerable amount of use of that spacecraft for a long period of time in the last 20 years or so. The 2 Galaxy spacecraft, we had a Japanese spacecraft that went off that actually died. That's the one over here. And that one was lost forever. And then this little Canadian spacecraft called Anik, which went offline for a while and was eventually recovered. Now that blue line and the big thick black line are a way of telling you how many sunspots there are on the sun. Not quite sunspot number, it's the one I use instead. But you'll notice that every once in a while there's not very many, and in between there's a lot. And the funny thing is, doesn't seem to be that you have to be when there's a lot of sunspots. They can happen pretty much anywhere they want. The other thing is, how much is this worth right here? It's $1 billion, $250,000 each satellite. That's an estimate, but it's $1 billion, and that's good enough. What else can we do? This is where I got into the whole thing. How much does it cost to keep the Hubble up in space? It's a shuttle flight. The shuttle has to go up there, it has to attach to the Hubble, and it has to boost it up. Why does it have to boost it up? Because even where the Hubble is, there's a little bit of atmosphere, and it slows the Hubble down, and it starts drifting down towards the Earth. It costs you about $500 million to $1 billion to do that mission. They got me onto a committee. They said, do we need to fly 1 more mission to reboost the Hubble, or 2? We want the Hubble to stay up there till 2020, 2025. And our answer was 1. How much did we save the American taxpayers? $500 million, $1 billion. So when I asked for my finder's fee, I said, 0.5%, 0.1%, that'd be fine. I was told that I should be happy I was employed. A more important example is the ISS, because it's falling roughly 2 kilometers a month from its orbit towards the Earth. That means it's at 350 kilometers now. At 150 kilometers, it's toast, because it gets really hot, and it will fall back in. So you only have about 100 months. That's rough, and if you know better, that's great. But you only have years where that thing is going to be able to be stable before you have to go up, plug back onto it, and boost it back up. Again, it was a shuttle flight. It's $1 billion. I'm going to skip that. Okay. But the thing that's been really cool is that, I work for NASA. We care about satellites. We should. That's our job. You guys live here on the ground, right? And what do you care about? Electricity, GPS, TV, gasoline. I can only handle one of them. I can talk about electricity. One of the major concerns that we have with space weather now, with those particles coming in and hitting the Earth, is that it interacts with our electrical grid. And we have some really great examples about how that is a problem. One thing, first off, how many people here know how to generate electricity? You take a magnet, put it in a coil wire, spin the magnet around, you get electricity out. That's all you need to know. Magnet, coil, wire, spin. That's it. There's our generator. That's not quite good enough. We need to get it to us. And so what they usually do is they run it through one of these transformers. These transformers are the size of your house. And it steps up the voltage so you can put it on the lines and send it to us. And we love it because we think electricity is great. Okay, here's an example. This is not space weather. However, this is the problem that we're worried about. A little while ago, 2003, August 2003, somebody took out the wires. Okay, in a place in Ohio, the wires were so oversubscribed and got so hot, they drooped down, touched the ground, and zap, took out that transmission capability. Electricity is really weird. You can't store it. Electricity, once generated, must be used. And the electricity that was in what they call the Lake Erie Loop had to go somewhere. So it went counterclockwise for a while, and they figured it couldn't do that, and went clockwise for a while. It eventually brought down the entire loop around Lake Erie. That's Canada, Ohio, Indiana, parts of Illinois, New York, on up into Maine, and other parts of New England. That's not good. That's because they took out one wire. If the same thing happens during a time of space weather doesn't take out the wire. Space weather takes out the transformer. It blows up transformers. We have good examples of this. I'm not going to show you the pictures, but the whole transformer will just blow up. That's the size of your house. Oh, it disappeared. There. That's the size of your house, and it's gone. Takes about 3 months to replace, and the problem we are worried about is with one of those transformers goes away during, say, August 2003 type conditions, we can lose entire parts of the electrical grid. These happen on small scales. They typically happen in the northern latitudes. It's not really a problem if you live in Alabama, but the way our grid is working nowadays and the way we oversubscribe our lines, especially in the summer months, the sensitivity to these small things, taking out one set of wires caused a massive blackout in 2003. Taking out a couple of these transformers might do something similar in the future. However, I'm not predicting that will be soon. Another reason, I watch TV. Okay, Sheldon, the guy on the right. This is a very realistic show, by the way. I mean, some of these people they're so close to people I knew in graduate school. It's painful. I don't know where the pretty girl came from, but the interaction of the people on that show is amazingly close to what graduate school is like. He goes out for a walk for one reason or another. He comes back and he says he was lost, and they said, "But you use your GPS." He said, "No, there was a solar flare." I mean, that's a joke they think that people in the United States are going to get. And that's because the space weather and the way the sun interacts with our technological life is supposed to be something everybody knows. It's in The Simpsons. It's in The Big Bang Theory. It's in something called 2012. Okay? I won't ask how many people have read this book. I will never read I'll never pay for the book. I'll borrow it from the library. But in this book, Apocalypse 2012, and many of these other follow-on books and people that are doing this, they talk as if the upcoming solar cycle is going to be of such activity, it's going to wipe out life on the Earth. Okay, that's not true. Okay, the next solar cycle is going to be kind of a wimpy one. All right, but even if it wasn't, it's not going to wipe out life on the Earth. Okay, and just because the Mayans ran out of rock to put their calendar on does not mean that we're going to have an unbelievably active solar cycle 24. Okay, but all of this means that thinking about solar activity has moved from being the esoteric study of people in Hawaii to something that we see in our more or less our everyday life. It's important to understand it. It's important to gather data about the current state of the sun. That's why, and it's important to be able to predict the future. The people that do satellites and the power lines, they want to know what's going to happen in the next couple hours. The people that do satellites want to know a couple of weeks, or know what happened a couple of weeks ago when their satellite blew up. So they want to know information more quickly. Other people want to know what it's going to be like in years. That's where I come in. I like to try and figure out what the sun is going to be doing 5, 10 years from now. It's a lot of fun. It's really hard to prove yourself wrong because you got to wait so long that by the time it rolls around, they might have forgotten. But believe me, they haven't. Okay. But nobody uses tarot cards, crystal balls anymore. We use computer models. And what we really want to do is build a model of the sun's internal way of generating magnetic field. Now, it's the opposite of generating electricity. To generate electricity, I take a coil of water, stick a wire, stick a magnet in it, and spin the magnet, and I get electricity. To generate a magnetic field in a wire, I run current through the wire and magically get a magnetic field back out. They're amazingly backwards. Okay, we have a lovely example of that. We have a solar dynamo model that shows magnetic field. You're going to see those are sunspots going around. It opens up, and then those lines are how we represent magnetic field. This is just exactly like what you did when you did the iron filing thing back in school. You put a magnet on the ground, you sprinkled iron filings on it, and then the teacher said, no, put it under the paper first. And you had to spend all that time scraping the iron filings off. It's exactly the same thing. We're tracing the magnetic lines of force with the iron filings. We're tracking it with a slightly more expensive computer. And those, you'll see where most of the lines are. Lines being close together means a strong field. Lines being few and far apart being a weak field. Where's the strong field? It's all down inside the sun. The stuff that you see at the surface is just kind of like these random things that stick out every once in a while. And so the problem of understanding the magnetic field of the sun, which is what generates sunspots, which is what generates space weather, comes down to figuring out what's going on inside the sun. Hence, that's what we're trying to do. Hence, SDO, the most beautiful spacecraft in the world. SDO was launched a little over a year ago, February 11th, 2010. On an Atlas V from the Cape Canaveral base down in Florida. We're currently in an inclined geosynchronous orbit, and don't worry, we're going to show this all in a minute. Okay, there's the instruments, and that's all the details. There will not be a test. And this is where we need sound. Every mission needs a countdown.
3, 2, 1, 0, and ignition and liftoff of the Atlas V with the Solar Dynamics Observatory, learning why our star is changing our lives.
Now remember the sundogs I showed you. You're going to see bits of one in a minute. Right there.
Outputting levels.
all those waves.
Flowing as
That's a
expected.
sundog.
Everything looking good.
And then that was it. It was a perfect launch. It was a great day. I mean, you guys were up here, 4 feet of snow. What was your complaint? We had a perfect launch. It was, it was actually a lot of problems because when we do a launch at NASA, and I can't speak for anyone else, we do a launch, somebody throws it up into space, and at some point they get tired of it, they throw it, and they knock it off. And at that point, they're done. If you want your satellite, you got to get control of it. It's up to you. The launch people are done with it. And our people that took control of the spacecraft were here at Goddard during that 4 feet of snow. And if they had not been able to be there, sleeping in that building, waiting for us to overcome some high wind problems, we couldn't have launched. We actually, phone calls were being made. You guys going to be able to be there? But that was fine. This is our orbit. And this is a very nice depiction of it. You can see this, everything's moving. This is roughly the beginning, it's the middle of our eclipse season. You can see that we move far from the Earth. We're almost geostationary. We're inclined a little bit. So we don't get to sit exactly above the same point every time, but we do very closely. But every once in a while we go behind the Earth and we have an eclipse, which is what we're doing in the current time. That orbit looks like that if we trace it out on the surface of the Earth. Looks like an elongated figure 8. And it's at roughly the longitude of Las Cruces, New Mexico. And so we have put 2 antennas there that do nothing but watch SDO and bring the data down continuously. Why do we do that? We do that because we have what can only be described as a fire hose of data coming down to the ground. And we did that because we've learned with time that if we look at the sun, little bits of the sun, but look at it really a lot, that we'll see something happen and we realize we should have been looking over here too. Something happened over here, came into where we were watching, and we don't know what happened over there. So we take pictures of the sun, the whole sun, as best we can all the time. When we opened up the lights of the one instrument, this is what we saw. Or excuse me, when we opened up the doors, cooled down the CCDs, this is the first set, some of the first sets of images. I mean, we took 1,000 or so that day. So this wasn't really you should be continuing. Ooh, I just crashed my computer. Okay, what I'm going to do is shut that down and reopen. Because this is a Mac, they never crash. Yeah, but Keynote doesn't work much better with these movies. Okay. This has happened before. Just a second. That's okay. I gave a whole talk at the launch without any movies. None of them worked. Okay. And I know there's a better way to do this. You don't need to tell me that. Okay. This is our first light images from the AIA instrument, which is taking pictures of the sun in 10 mostly ultraviolet wavelengths of the sun. This happens to be the wavelength of a line of helium that's had an electron removed, but really all you really care about, it's helium. And as you pull back, you can see why we want to see not only that little bit in the upper right, but we want to see the rest of the sun as well. Because the whole sun is interesting when you look at it in these wavelengths. And the ability to zoom in on something and see the detail we get with the AIA and HMI, and then pull back and see what happened in the remote parts of the sun that could have influenced what we're looking at, is a valuable part of this instrument. And it's unparalleled time dependence and full disk, and it's a great instrument. And it works pretty well too. Okay, now I'm gonna do a riff for a minute, because so many people accuse me of lying to them. They tell me I'm using false colors. Okay, I'm not. Okay, the colors that you see on any image from the Solar Dynamics Observatory, they're not false colors, they're just lies. Okay, in general, you can't see the light that we're trying to show you. If you want, we can show you, we have 36 million images from our spacecraft right now. I can show them all to you in black and white. Would you like that? Or would you rather see that cool orange that I showed you before? Okay, so let's just go through and look at the different colors that show up from the SDO spacecraft. They're in an order of increasing temperature. Now everybody knows temperature, right? In here, the temperature is, what, 70 degrees or something like that. The temperature on the sun starts at about 6,000 Kelvin, which is almost 10,000 Fahrenheit, and it goes down a little bit. That doesn't really count. But then it goes up a lot. It's going to go up to 20 million Kelvin. Okay, it's really hot. All right, and okay, some people like to know that. Okay, and the other thing you're going to see is that we have gotten into the practice of never showing you an image. You're going to see a couple images now because it just didn't work the way I wanted to do this. But you're going to see a lot of really funky stop-action movies because we have so many images, we just put them together and make movies out of everything. I mean, that's the cool thing about SDO is that in general, we have we can look at what happened and what happened before and what happened afterwards, and we're going to show it to you because that's what we're doing now. Okay, that's the sun you're used to looking at, right? Now, I told you every one of these colors is a lie. That should be blue. Okay, but most people would not like that to be blue. They want it to be yellow, so it's been made yellow. Okay, that's 6,000 Kelvin. You can see a couple of sunspots. Think of those as eyes. Okay, there they are again. This is a little cooler. This is a little higher in the atmosphere of the sun, and it's a little cooler, so it's pink. Okay, now we start getting a little hotter, 10,000 degrees. You can still see the eyes, and you can start to see something happening in the southern hemisphere. And now let's get a little hotter. That's that orange that we showed you before. That's about 50,000 Kelvin. It's almost 100,000 Fahrenheit. Well, something is happening down there. That's pretty ugly. Okay, it's still got eyes. Now it's got an ear over there too. Got a mouth. This is the old man in the sun. Okay, this is something, I have the temperature down here so I won't forget. 600,000 Kelvin. Here we are at about 1 million Kelvin, 2 million Kelvin, 2.5 million Kelvin. We really like million Kelvins. I hate MK, but I use it anyway. 6 million Kelvin, 10 million Kelvin. Oh, what's that? Who ordered that? That is what we really want to measure. That's the magnetic field of the sun. If it's white, it's magnetic field that's pointing towards you. If it's black, it's magnetic field pointing away from you. How many people would want to get a compass and try and walk around on that? Okay, all the physical impossibility things aside, if somebody handed you a compass and said, go navigate on the sun, what would happen? I mean, your compass would just go crazy. It would be pointing north, you'd walk over here, it'd be pointing south, you walk over back over here, and the magnetic field of the sun is unbelievably complicated compared to the relatively smooth field that we have here on the Earth. And that's why we continue to study it now, 100 years after it was first measured. And we still don't understand where it came from or where it comes from. And we continue to use better and better instrumentation to try and understand that. Okay, here's the sun today. I made these this morning. I downloaded several hundred images from SDO. I put them into some software and I made myself a movie. You can do that too. I didn't get any special data. This is data available at our website. And you got to do some programming. You have to get some work into it. But I would like you to just look at compare the right and the left. And you can see one of the things that we spend a lot of time doing is seeing what's on one side that's not on the other. Because on the one side, it's 50,000 Kelvin, and on the other side, it's about 1 million Kelvin. That's to a large extent, the only difference is the temperature. And so understanding the differences that the sun has at these different temperatures is one of the things that we try to understand using this data. And, you know, and you can just look at it for a long time. It's quite pretty. I mean, you can almost see lightning on the sun as you see these loops light up, and especially when they go between two of the active regions. If you watch over here for a while and over here, you'll see that. The orange is where we have these enormous prominences erupt off of the sun and they take off. There's one of those happens early in the loop. It's on the down here. You can see it's right over here. By the way, that thing that's coming around, that's the man's mouth. The movies we saw earlier were from December, and here that structure is still around. It's been around since last October was when it first formed, and so it's still there. Something very stable in the sun. It's kind of odd to have that kind of feature, but it's the cool part about this solar cycle. Okay, why did we build AIA? We built AIA because we could. CCDs have come a long way since the early 90s, and we were able to build these enormous, large CCDs that now, a couple years later, you can buy for $200 in your camera and take pictures of me with your little red eye thing. Okay, the CCD development has been very rapid, but this is an idea of what we have gained. SOHO was launched back in 1995. It was considered pretty close to state of the art for what they were doing at the time. Since then, we developed HDTV. We flew another spacecraft called Stereo. You can see considerably, you're going to get better definition simply because it's a bigger picture, just like you get better definition in HD than you did with a standard television. And now we have the SDO images, which are bigger still than the ones that Stereo flew. We get superb pictures out of this spacecraft. And one of the things we can do is look at very small details. And this is a flare that took place, I believe this is a Valentine's Day flare. We call it the Valentine's Day flare because we were up at 10 o'clock at night looking at it, but it actually, the UT was the next day. And the flare is actually this little brightening that happens down here. It's just that little ridge of brightening that happens. It was cool because it was the first time the sun had had a flare this bright in 6 years, 5 years, so we were pretty happy about it. But the cool thing was, it had a little puff. See the smoke ring come off the sun? You have to watch for a little while, but you'll see the little puff, a little smoke ring come off the sun. Let's see if I can trace it out. Right there, you can see it right there. Okay? Now, when those things burst off the sun, they follow what looks to be like a stream, and they go out away from the sun. And there's a couple of ways you can see that. You can see one going that way. You can see one going that way. What's it going to look like if it's going that way? It's going to look like a smoke ring coming right towards you. It's called a halo coronal mass ejection, or halo CME. And here is one right here. The first X-class flare of solar cycle 24, and what do we have? A halo CME, which says it's coming right towards us. It lit up the internet. Might have melted some wires. People were so into this 2012 thing that I got an email that asked, is the world going to end? And I wondered, why would anybody send me an email asking if the world's going to end? If the world's going to end, shouldn't you go out on the last date or something? I mean, crazy people. Did the world end? I got that one too. Did the world end yesterday? You put your name on a NASA website, you get a lot of good email. Okay, this one, can you see that smoke ring? Okay, this one is our first halo CME. Some people would say it's a failure, it didn't hit, and it didn't cause the end of the world. I thought it was a pretty good success. We saw it. Everybody, we knew within a day it was a halo CME. Everybody that worries about these things was up and watching. This one happened to be inside pitch, high and inside. Okay, it's a little bit behind us and a little bit above where we orbit, so it missed us. We got some beautiful aurora out of it, but nonetheless, it was a miss. And that's okay. The world didn't end, and we can continue looking at our pictures. All right. My favorite. So far in the mission, I get to pick my favorite one every once in a while. This is my favorite. I call this the trebuchet Prominence eruption. You can call this a lot of things. I mean, there's the vacuum cleaner at the end. There's the trebuchet. There's the flamenco dance skirt going this way. And then at the end, there's the vacuum cleaner sucking it all back in. I mean, this has got everything. It's a great picture. And now, I mean, just watch it. You can just, we sat there and watched this when it happened. When Barbara made the movie and when we started watching it, we just watched it for like an hour. Because there's so many things happening in that movie that you just want to try and explain, and we haven't yet. Because we're too busy watching movies. Okay, you know, and now you know why it's orange. Because what are trebuchets used for? They're throwing pumpkins. See the pumpkins over here? Isn't it the right color? Okay, trebuchets have made a big comeback because of pumpkin chunking. And having grown up in Delaware, I'm happy and proud to know that something besides DuPont has happened in Delaware. All right. The second, there's three instruments. I've talked about one almost exclusively. We have another one called HMI for Helioseismic Magnetic Imager. That's going to look at pictures of the magnetic field, but it also is the magic instrument. Remember I said I want to look inside the sun. I can't do that. I can't go dig a hole inside the sun. It's gas. It would be very difficult. It'd be like digging a hole in the ocean. Okay, but you're not allowed to put anything around you. Okay, isn't this the best data you ever saw? Thank you, Peter. These are Dopplergrams. The godfather of Dopplergrams, a guy named Phil Scher, who has seen his share of Dopplergrams, once said, if you've seen one Dopplergram, you've seen them all. Are you tired of seeing them? These are waves in the solar atmosphere. And the amazing thing is that even though these started off as noise that people valiantly struggle to get rid of, such as Peter, to study other more important things, those waves are the holy grail for looking inside the sun. And you're going to have to accept it because the 12 pages of algebra necessary to get from this statement to the next slide, I think I can skip. Oh, thank you. I can look through the sun and see the other side of the sun. And here is an example. These are spots on the Earth side of the sun. This is a spot kind of on the other side of the sun. I don't know if it counts. And there's nothing on the far side of the sun today. Yeah, that's just the way it goes early in the solar cycle. But if we go back in history and look at different far side images, we can actually watch spots rotate from the front of the sun to the back of the sun and then, come back around. What a great thing. You want to predict what's going to happen in 2 weeks. Remember that was one of the requirements I talked about earlier. They want 2 weeks. The sun takes 2 weeks to rotate halfway. Being able to see the back side, the far side of the sun, allows you to do that. It's a great thing to be able to do. I just hope that something happens back there soon, because right now it's pretty boring. The other thing you can do with that same data, but if you give it to another clever person, and they use a lot of computer power, is they can actually go in and discover how the sun is rotating down inside the sun. Now, we're not really sure what this tells us yet. It tells us something. It tells us this. It tells us this cool pattern of bands moving in the sun. And if I look at these bands, this is mostly SOHO and data from a ground-based network called GONG. You can see this little thing right here, this little edge. And here's another edge coming out later, and that's solar cycle 24. When people were talking about solar cycle 24 not appearing, we're going into another Maunder minimum where there's no sunspots. We're sitting back there smugly saying, we see solar cycle 24. It's already here. Okay, we knew it, and sunspots showed up right there, right at the bottom of that layer. That's pretty cool. We don't know why yet. I know there's people that work on this all the time. This is a great thing about helioseismology is it's giving us information we don't quite understand yet. We know how to get this information. We don't know exactly what it's telling us about that solar dynamo, but we know it must be important because the sunspots know about it. The sunspots appear along, no further, they all appear above that little line right there. They don't appear down here. They all appear up there. The sunspots know to appear where that river, that little current is in the sun. That's cool. If you know where that is, then you can make a prediction. Unfortunately, it takes about a week to do the data analysis, so by the time you have the data, you already saw the sunspots. So it's not really a great prediction right now, but there's something in this information that tells us how that magnetic field is made and how it's being moved around inside the sun. This is our first way to see that model I showed you of the solar dynamo. We're seeing it. Now, unfortunately, we don't get what we really want, which is that magnetic field, but we might get that soon too. But we got something. We're looking inside the sun, for crying out loud. You can't do that, but we can. Okay, we also look at something called the vector magnetic field. If you wish, you can call this the hedgehog movie, or moles, if that's your problem. And those are, remember the black and white picture? It just showed us in or out. This tells us which way the field's actually going. How would you like to have a compass in that magnetic field? I mean, it's just all over the place. Once again, this is our research trying to understand how that field is generated, how do we actually measure it to some extent, and how does it make flares? How does it make those times when the sun says, "I'm tired of this prominence," and just throws it away? Calls it a coronal mass ejection. This is the future, and we're going to get there. Okay, I'm going to show you one more movie. This is the magnetic field boiling up from inside the sun. If you didn't think the magnetic field, if you thought the magnetic field came from outside, and you want to be convinced, just watch this for a little while. You can't see the black very well, or I can't from here, but you can see the white. You see white field just boils up in here, and especially in this area. It just comes up from inside and then moves over there somewhere and gets stuck in some places that maybe some people would like to study. We have black over here as well. Those are opposite sides. Remember, white is pointing towards you, black is pointing away from you. And so here's the black, and here's the white, and then this will loop back. But this is some little active region. It's a very tiny little active region on the sun. Probably never developed a sunspot, but it's the field boiling up from inside the sun and then getting moved around, pushed around by the velocities near the sun to make a little active region. It's great to be able to do this. It's the time resolution, being able to take the really fine pictures and make this data that allow us to study this kind of stuff anywhere on the sun. We have instruments that could pick a particular place and watch, but what we can do is just look and then go in and carve out a place that looks interesting and study it. So it's a great benefit to the people that study the magnetic field of the sun. Okay, my question to you, I hope there's a person in here under 21. You saw that in 400 years, we went from drawing on paper, which by the way, we still do. People every day that they can go out to a telescope, put a piece of paper inside of a telescope and draw the sunspots, just like Galileo. A little bit more sophisticated, they use color, but it's nonetheless, they look very much the same. We have those photographs. We have what I call the H-alpha picture, the ones of hydrogen. Now we have the pictures that we can take from AIA. These are taken from space, but they are very exquisite pictures. What are we going to be looking at solar cycle 25 with? I mean, the way technology is changing, the computers that we use, how do we pick who gets to look at the sun over the next solar cycle? Because this is how we're going to look at it for this one, by the way. I mean, we have a 5-year mission, 10 years we think we can do, and with the last estimate, we had 900 years of propellant left. So we have enough fuel. But look, I mean, this is a spectacular time, the August 1st double prominence eruption. There's a flare. There's all kinds of that stuff where you're looking at something and something propagates in, and you really want to be able to see the whole sun to understand it. So here we see the whole sun. We can see everything happening, and we still don't understand it. But give us time. Okay. I would like to take questions. But first, I would like to tell you, you too can download SDO data. People do it all the time. It doesn't hurt. If you want a lot of data, it's going to cost you another disk drive. Okay, we get 1.5 terabytes of compressed data a day. That goes out to about 2 terabytes of uncompressed a day, and then we store it all. Petabyte of data a year. Okay, this mission is made possible by small terabyte-sized disks that you can buy for $100. You just need a lot of them. All right. We also have a presence on Facebook. We have a guy out in California who's very enthusiastic about sharing what he thinks about SDO and the rubber chicken that I'll let you discover. We have a good Twitter group that talks all the time. It's especially oriented towards educators. If you're a teacher in the audience, they accept questions and have discussions on how to use SDO data in your classroom. They attempt to make it fit in the classroom, not just a substitute, or as a substitute, not just something different. So we encourage you to go look at our data, have a good time. It's a great satellite, and we're very privileged to have built it and run it. So thank you. Okay.
So, questions?
So, given all that this satellite can do, do you really see any merit in manned spaceflight, or do you think we should simply maintain a larger robotic presence in space?
So I got the manned spaceflight question again. Manned spaceflight is a different beast. Okay, the stuff that we do requires spacecraft to live a long time in space. And we build them to not require fixing. If they get broken, then we're in trouble. Manned spaceflight is an entirely different beast. Just living in space is an adventure. And so I think you need both. You need to, remember, we have the billion-year problem. We're going to, in 1 billion years, we're going to have to leave the planet. So we have to figure out how to do that. But, all that aside, the exploration imperative is still there. And so I actually like going to an asteroid. I studied meteors in planetary atmospheres. They derive to a large part from asteroids. So I think visiting an asteroid is actually a cool thing. And a lot of people say if we're not going to Mars, we're wasting money. But I think going to an asteroid would be a cool thing. I think that we need an aggressive robotic program as well, because that's what we can send to Pluto. And that's what we have sent to Pluto. So I think you need both sides.
Why does space weather take out transformers? I've been to Westinghouse, Muncie. They're huge.
Excellent question.
They're also encased in steel. Don't you have a
Okay, how does
What?
space weather take out transformers? Okay, how do I generate a magnetic current? I stick a magnetic field in a wire loop and I spin it, and that produces electrical current. When I have space weather, so we'll just talk about one particular type, a very strong aurora represents a current that's above the wires that are moving electricity. That current makes another current in that wire. That current goes back into the transformer and cooks it. Yeah, so do I. But it's just that. It's just the reverse process that we had before. You have a current, makes a magnetic field that affects the wire, and that drives a current back into the transformer. So it's actually a very simple process. It must be simple because it really does a lot of damage. There's nothing sophisticated about that.
Way in the back? Yeah.
Why is this solar cycle 24? What are you counting back to?
Why is this solar cycle 24, and when did they begin? What are you counting back to?
We have evidence that the solar cycle has been around for actually quite a while, even 10,000 years, quite well, and possibly as far as 100 million years. We started solar cycle 1 when the guy found data. Okay, he didn't have the advantage of knowing what to look for that we have now. So he had to give it a number, or he had to give it some designation. He could have called it solar cycle alpha, beta, gamma, but he didn't. He called it solar cycle. Pardon? It was Wolf, and he actually started his in the middle of the 1700s. It's about a 250. It's an 11-year cycle. We're in cycle 24. That's about 250 years. So if you go back about 250 years, that's where the first one was. So, and it's totally arbitrary, but he had to do something so that he could talk about it in letters. And it was easier to call them cycle number 1, 2, and 3 than it was the solar cycle between 1722 and 1736. It was just easier to write like that. And that's quite common in science, to have some arbitrary coding in things like that. And other than that, there's absolutely no significance to the number.
Yeah. Do you have a projection about how the sun's output might vary enough to affect this planet?
Well, at the current time, the sun's output does not appear to vary enough to affect the climate significantly. The sun's output creates our climate. It's just whether the fluctuations are sufficient to drive the temperature changes that we see. There is evidence that it does in the past. The second part of the evidence is whether or not it can drive what we're seeing in the present. And we have to be very careful. We have changed our atmosphere in the intervening 50 years or so. And now we have an atmosphere that has a different loading of radiatively active gases such as carbon dioxide and methane. And so we have to be very careful when we ask that question. At this time, it appears that the sun's output is not very enough to explain what they measure today. But it's a subject of active research. We would certainly like it to be true, but because that's what we study. But that's a very biased point of view, and there's a lot of things going on, and to throw away one to the advantage of another, I think, is incorrect.
I'll go over here.
Well, technology is. Go ahead.
Given the SDO mission, is there anything else you'd like to see on the next spacecraft, and what do we do next?
Well, that smoke ring, we don't have the instrument that made that smoke ring. We had to take that data from SOHO. Now, the advantage is we have SOHO running. So we have multiple spacecraft out making measurements that are not being done by SDO at this time. And there are numerous instruments we wish we could have put on there. You just can't put everything on these satellites. The big thing was our data rate, and to get the instruments on to do the high image rate that we have. It would have been nice to have a coronagraph. We didn't. But I think that in the future, people will build better coronagraphs and put them out there anyway. So we will have the coronagraphs. We already do. We have them on stereo. They have much better coronagraphs. So it's mostly more you have to define what science you want to do before you can come back and say what instruments you would like to have. And that's how we design a spacecraft. What do you want to learn? These are the instruments we have available. Can we build it? And at this point, we haven't started designing the follow-on to SDO. SDO is a follow-on to SOHO, to some extent to stereo. Stereo is unique because of its orbit. But certainly SDO is a follow-on to SOHO and its imaging instruments. And we don't have anything on the board to replace them at this time. But there are sensors that we really like to do. If you look at that flare, you saw that X pattern around it. There's better ways to do a telescope so you can see the thousands of times brighter at the middle and still keep the dim stuff out away from it. That's one of one issue that could be solved.
How do you see the far side of the sun? Are you going through the core? How do you see the opposite side? Far side.
How do you see the far side of the sun?
I told you, it's the magic instrument, okay? How do you know an earthquake happened on the other side of the Earth? We get seismic waves that come from that side of the Earth. We don't quite get it like that. But what we do is we see a wave headed that way, and then we wait. We know exactly how long that wave is going to take. And when it gets here, it's a little late. That means it slowed down on the far side. We look at a whole bunch of waves going that way and watching them come around this way, and if they all slow down, but then a group of them start being normal again, then we know something about this big was slowing them down on the far side of the sun.
What kind of wave is
These are pressure waves. These are sound waves in the sun. That's the ripples that you saw in that Dopplergram are nothing but these waves going all over the place. And you just and you pick out a set of them and you watch them go around and come back around. It's a amazingly powerful technique that is not obvious at all how it works. They get better at it every day. So the image you saw there is much better than the ones they were doing 10 years ago, and it was not being done 20 years ago. So it's a very new technique.
Yeah.
What other organizations were involved? Is this a Goddard thing from beginning to end, or are there academics, and who actually built the spacecraft?
The space.
What organizations were involved? Were there people from universities involved, or was it strictly Goddard, or who's involved?
This is a mission from NASA. It's not a Goddard mission. This is a NASA mission, and it was built at the Goddard Space Flight Center. The instruments were built by 3 different groups. The EVE instrument, which I did not talk about, was built at the University of Colorado, at a facility they have there. The HMI and AIA instruments were built by a group at Stanford and a group at Lockheed Martin out in Palo Alto, California. So they were, and now those 3 groups run the instruments. So Goddard runs the spacecraft, and then they have coming in on the network, the instrument team send the commands to control their instruments. So it was a partnership between Goddard and the 3 instrument groups in California and Colorado.
Great. And I'm going to go way up here. Yeah. Okay. Great. Didn't see you. How far is the spacecraft from the sun, and how close can you get it to the sun?
Okay, we're spoiled. Okay, we really like being 1 astronomical unit from the sun. We're used to it, our electronics are used to it, our solar cells are used to it, and that's where we are, 1 AU from the sun. We orbit the Earth. We go a little tiny bit closer to the sun, but it doesn't really change anything. We're not really that much closer to the sun. It's just a little tiny bit. So we actually are going around the Earth. We do not, so we don't get any closer to the sun. It's a great place to be. If you go close to the sun, it gets really hot, and that causes problems. So we stay where our instruments, we're taking pictures, and so we want to take pictures about the same distance all the time. So that's why we have the orbit that we have. Oh, that didn't work.
Yep.
I lost the network.
You showed a couple of pictures, a couple of little films that were fabulous with material being ejected out of the sun.
Uh-huh.
And it looked like there was a structure that was kind of hoovering it back in. Is that an optical illusion, or what's going on there?
You showed some pictures with material being ejected, but it looked like there was structure as the material was flowing back in. And what's going on there?
Okay. Let's go to the video. Everybody remembers that guy, right? Let's see if we can find that. That was the trebuchet prominence, right? Yeah, that was the easiest one to see that in. So let's go to the slide before that. Okay, so now we start. Remember I said there's at least 3 phases. The poor thing's working like crazy nowadays. There was at least 3 phases. There was the initial ejection where the material was shot away from the sun. Okay, then there's the billowing phase, whereas it's moving to your left, right? And so you see it billowing, and then at the end, it is being pulled back down onto the sun. Okay? Into that same spot. And that's, in this case, that material did not leave the sun. So if you want it to hit the Earth, it's got to leave the sun. And in this case, some material may have left, but a large fraction of it got out there, wasn't moving fast enough to escape from the sun. It's sitting in a magnetic field, which is causing it to not be able to move straight out. And then it stops. And once you stop, it's like a shark. Okay, if you are trying to get away from an object in the solar system and you stop, you have failed. And in this case, it just comes back down. And then this is described by various people that study this on how that material comes back down. So you're right, there's that phase as well. It went out, didn't make it, and it had to come back down. It's being sucked back in.
Something unusual about that feature on the sun that's pulling it back?
No, we actually see that quite often in an erupting prominence where it'll come back. And I believe if you look carefully, maybe not in this one, but in the first light prominence eruption, you can actually see that it left one spot on the sun, and when it came back, it goes back in on another spot on the sun. So, pardon? Gravity is pulling it back, yes. Gravity, the escape velocity from the sun is 700 kilometers a second. If you ain't moving it, if you're not moving 700 kilometers a second, you're coming home. And this stuff wasn't moving that fast. We made some estimates. This was moving like 100, 200 kilometers a second. So it's not anywhere close to getting off the surface of the sun.
We'll do one or two more. I'll do one down here.
You said the smoke ring missed us last year. We dodged the bullet. Any sense of what would have happened if it had hit us?
It was a small. Okay.
You said the smoke ring just missed us, I think, above and to the left or so last year. Any sense of what would have happened if it had hit us dead on?
This is in February. You know, the big problem with the power grids is really during the summer months when the transmission lines are oversubscribed, the generators are all running flat out. And so if you go in and take some capacity off, it causes a problem. This is in February. You know, it might have caused a small power outage somewhere, but not nearly the trouble that we see in the late summer. And, you know, it might not have done anything. It really depends on what happens when that smoke ring comes and hits us. And just the way it comes in and hits the magnetic field of the Earth and how that responds. And so each one is a little different. So I wouldn't have predicted, this one would not have been a dire effect. This would have been a fun, it made some nice aurora as it was, and maybe there would have been a small magnetic storm.
Okay, I'll do one more way up here.
Huh? Yes, ma'am. And the amazing thing is that they're sitting right next to each other. Okay, that was a long question. Okay.
I'll repeat. In the different wavelengths that you showed, the sun has a totally different view, and why is that?
Okay, there's a couple things going on. One is on the left, all you see is bright stuff. It's hot. On the right, you see bright stuff, but you also see stuff that's suspended above the atmosphere of the sun, and it's reflecting. So if you look over on the edges, it's hard for me to know what you can see up there. If you look over here in this corner, over here, this prominence right, this stuff right here, some of that is emission, but a lot of it is it's simply reflecting light that came from the sun. It's headed out, and it hits that, and it gets reflected, so we see it. So a big difference in the two is that reflected light versus just the hot emitted light. And so that's one of the big differences. But the other is one's helium, the other's iron, and they're just at different temperatures. And that actually is an important part of it, is that there are different temperatures, but they are right on top of each other. And how do you keep one cold while the other's hot? And you actually do see cold material embedded down inside the hot material. So it's all twisted up together. It's a great problem to study.
Great. Thank you very much, Dean.
Okay.
Really appreciate it.
Okay. Thanks for having me.
I'd also like to once again thank Aerojet and NASA for their support of the series. And mark your calendars. Actually, it's only in 2 weeks. On April 7th, Alfred McEwen will present Mars, a Dynamic World. He's been looking at the highest resolution camera ever to orbit Mars. It can take pictures of things about this big from orbit. It's cool. Be sure and come to that. That's in 2 weeks. And I'm not sure if the observatory is open. It depends on the weather. No, too cloudy. Okay, it's also too cold. But the most important thing is fill out your survey, because you will be in then for a drawing for a $100 gift certificate at the DC restaurant, DC3 restaurant up on Capitol Hill. And it's a very appropriate that this museum patronize that restaurant. So anyway, fill out that survey, and we'll see you again in 2 weeks. Thanks for coming.